Good morning, everyone. I'm going to start off today going back to the example from last class, right at the end. I did get it to end up working, but only sometimes, so not exactly sure why still, but we may have to run this a couple times. Just as a quick reminder, we're looking at something like this, where we had run a linear model and a polynomial model against some made-up function that looks something like this. So the red line is our linear, the blue line is the polynomial function, and then we are going to create a piecewise segmented model. Okay, which I may have to run a few times. Here we go. So here, it's just a small number of segments, so you can see where the breakpoints are sort of located at every kink in the line, here, 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 here. And the way this is done is fairly simple. It takes all of the points in between the breakpoints, and it runs a separate linear regression, and we end up getting something that looks like this. Okay. Like I said, both the piecewise regression as well as the polynomial regression are a little bit less common in practice. And we're going to see the more common iteration and usage of these approaches today. So we'll start off talking about that. Okay. So today we are going to talk mainly about splines. So these are a combination of the piecewise polynomial and polynomial. So piecewise polynomial functions. So you can imagine here that it is able to take advantage of essentially both portions of advantages in linear, or not in linear models, in the polynomial models and in the piecewise models, so that you should be able to sort of more closely fit against a line. So there are a couple, I suppose, hidden details. So let's take a quick look at what happens if I were to hypothetically put together a piecewise polynomial function. And we'll be sort of building this up to eventually get to a spline. So let's consider what a piecewise cubic function might look like. suppose I have data that looks something like this, and I have a breakpoint maybe somewhere like this. Your function may look like something like this. And so what you'll notice here is that you actually have what is known, we'll say at the breakpoint, you have a discontinuity, and that may make sense, right? It's not always the case that the lines are going to perfectly align. So this piecewise cubic is 2 cubic polynomial regression line segments. And then we may enforce a additional constraint. So if I take approximately the same data, and I have a breakpoint here, I could, in theory, do something like this, where they are now connected. And this would be known as a continuous piecewise cubic. So this is the same as before, but you have an additional constraint that lines must touch. Okay. And lastly, let's go with the same sort of data points again. You could have something that looks like this. And this is known as a cubic spline. And there is an additional constraint again. That lines must be smooth. Yes, hang on, I see a question in the chat. So it's constrained to x cubed, so it's called cubic. Yeah, I'll talk a little bit about that in a second. It is cubic, it's x cubed. I'm writing that because cubic splines are kind of the most common. Because once you start doing this sort of thing, you don't need to get to really high orders of polynomials to get really nice fits for any sort of set of data. So I'll talk about that in a second. So additional constraint that lines must be smooth. Okay, and so what does that mean? So technically it's when the first and second derivatives are continuous at cutoff. And when you have a condition like that, that is known formally as a knot. And so at the knot, if you have the second first and second derivatives being continuous, that's the additional constraint that gets enforced to be able to run this. Okay, so that is kind of visually what it looks like. You end up getting something like this. yi equals beta 0. These are known as sorts of basis functions. It is some functional transformation of your x variable that allows for this to happen. And so we're not going into detail about exactly what goes on in the basis functions. But essentially, when you have knots, you have a number of parameters where it's the number of polynomials that you have plus the number of knots. And as I was mentioning, cubic splines are the most common. We trade off the polynomial. So that's having lots of x to the n terms for more knots. Okay. So knots provide a lot of flexibility. And I'll try and draw an example of this. Consider hang on, let me draw it like this. So I'm going to show an example with different numbers of knots, and we can try and see what happens here. I'll try and copy this as best as possible. So if we have 0 knots and we fit our function through here, it might look something like that. And then suppose we have 1 knot. In theory, it might look something more like this. And if we have 2 knots, maybe I'll have something like this, where I would have something that looks like this. So in each case, as I add additional knots, then your fit essentially becomes more, it's going to fit closer to the data. So and this is a nice way and sort of complete departure from the more parametric models where we're sort of assuming the functional form. Here it is layering in complexity, right, into your basis function. And the more knots and the more polynomials that you're including in the spline, then essentially the more sort of curvy the line is. And by adding essentially these degrees of freedom, you can get closer and closer to the points in the data. And of course, right, this goes back to the trade-off that we've been discussing all throughout class, where as you increase the flexibility, you decrease the error term from bias, but you increase the error term from variance. And so same sort of trade-off that we've been talking about. Okay. Let's talk about a specific type of, we're going to talk about specific sets of splines and types of splines that people use. So we have what's called natural splines. So splines can have high variance in the outer range of predictors. And this is related to the issue with polynomial regressions in general having sort of large variance right at the edges of the data. I will share the screen again on RStudio in a little bit, and we can see that happening. So just keep in mind, you'll see it happening right on the edges. And so natural splines are meant to try and address this. So natural splines add constraints so that function is linear at boundaries. Okay, and so that might look something like, if I just have some set of data, the fits themselves are going to be fairly similar, but you may have let's see, a cubic spline may look something like this. For uncertainty in the fit, whereas a natural cubic spline will be a little bit tighter at the ends of the data. Actually, I should draw these ones a little bit closer. So at the ends of the data, you'll tend to see, okay, so for a natural spline, you'll tend to see a little bit of a difference between the range of estimated fit. Okay, and going back to what I was saying on the sort of last handwritten notes, so how do we choose the number of knots? So this is, again, same as the parameters that we've been talking before that help to develop the fit of the model, how close it is with the data, right? So if you have too many knots, then you may be overfitting the data, but if you have not enough knots, then you could be biasing your model. So this is chosen through cross-validation. Again, same sort of technique. I can, right, just as a refresher, I can vary the number of knots that I run the model against, and then I'll look at whichever one has the lowest out of sample mean squared error, which we obtain by doing something like a k-fold cross-validation. Okay. So let's take a look at an example of this in R. So we need to use a function from a library called Splines, unsurprisingly. Okay, I see a question. How does natural splines convert the edges to a linear fit? Yeah, good question. The natural spline essentially enforces additional constraints near the boundaries that I believe modify the basis functions, although I'm not 100% sure on that. And what that ends up doing is that as you it'll essentially segment at the same, it'll essentially add extra knots right at the end, and then the continuous function is going to be linear at some point, so that it reduces this effect here. This is actually a good reminder. So we were mainly looking at the green line for the segmented when I drew all of this out, but actually what I've done is I've also included a dashed black line, and that dashed black line is exactly the true function that we created, right? So that is this sine x cosine 10x plus 0.5x plus a deviation. So it's that minus without the deviation. So this black line is our true function, and you can see where the polynomial regression has some difficulty, right? So in sort of in the middle here, it's not quite matching. It does a pretty good job in other portions, although it might be underestimating in some parts where the segmented model may actually be getting closer in some parts, right? And then more noticeably, sort of at the edges, there's not so many points here, so you don't see it as much, but at the edges, you tend to get this sort of effect when you're doing polynomial regressions. And so you still see this a little bit in the spline example, but with natural splines, it'll help get rid of this sort of issue. Okay. I see another ambiguous question in chat. Is that a question? Splines too?
I don't know if Splines it's like Splines 2 is the package.
Oh.
If it says like it's not available on this version of R.
Oh, really? Let's see. Libraries. Well, it's works for me. Let me take a look. Really quickly. Splines 2. I'm not sure about that. I'll check that and maybe I'll write it in the notes or something. So check splines 2.
It might just be like a base package thing. Sorry, I might just be wasting your time.
Yeah, I don't know. It works for me, but it could be, you know, depending on your version of R. If you can't get the regular splines to work, let me know at some point. Okay. So the cubic spline, technically, we're still talking about a linear regression, right? So this is, if you remember when I was writing this out as a basis function, so what beta 0 plus beta 1 b1 xi plus, you know, some other stuff. And so this function here is some kind of transformation, but it's still in a linear model context, right? We're linearly adding some transformation of our original data. So the way that we write it in the linear regression model is we have this thing BS, which is the basis. And then we have to choose where to put the knots. Okay, and so in this case, I am going to go through here and I'm going to add a knot at every at an interval of every one. So I'm going to have one here, 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 here. It's essentially placing your cutoffs, right? And we'll take a look at what that looks like. We need to create a prediction. And I'll just run it from 0 to 5 at a interval of, say, 0.01. And I'm going to include the standard error. Okay. So let's go ahead and copy this part, which we've done. So this is going to actually include the other fits that we've done. Okay. And let's take a look at what this looks like. Where our y is now going to be our cubic prediction fit. And let's have a color equals orange. And I also want to include the standard error. So I'm going to do fit plus 2 times this standard error from the prediction. And I'm going to make that dashed. Yeah, sorry, I'm not using ggplot here. Okay, so let's take a look at this. Hopefully this will work. Oh no, okay, 1 second. It's from 0 to 5 by 0.01. Let's take a look at the model first. Okay. So these are the coefficients for each of the basis functions, which don't really mean anything because we can't interpret these to be sort of interpretable in relation to our original data. So that's why I don't even bother sort of showing that here. Again, as we venture into non-parametric territory, a lot of this becomes much more about prediction rather than inference. But let's see what's going on here. Cubic predict 1 fit. So there should be 1,000 points here. There seem to be twice as many points for some reason. One moment. .01. Let me make sure this is the same. Sorry, bear with me. Sometimes the random points can be a little bit troubling. Let's see, is this the same? Um, Sorry, this is unusual. I was testing this out this morning and it was working. Yeah, let's see. Okay. Okay. I guess it is still uh it's still going. Okay. So in this case, boundary knots, I'm not sure if this is actually exactly what I want, but let's take a look at what happens. So we've run this cubic spline, and it's doing a cubic function from here to here and here to here. It doesn't look like it's quite working, but let's try and modify this, and we'll increase the number of knots. So what I'm actually going to do is I'm going to get rid of the piecewise and polynomial portions. And we'll take a look at different different fits. Okay, so here I'm gonna, in cubic spline 2, in line 30, I'm doing the exact same thing as before, but I'm increasing the number of knots, the number of breakpoints. So this is, again, sort of increasing the flexibility here. And hopefully we can get this to work. It's giving me a similar error message. Actually, I think it must be because I'm starting at 0 here. Maybe if I try something like this. No, that's all right. We'll just leave it as is. And hopefully it'll still be working. Yeah, okay. So we can see what happens when you have, when you increase the number of knots, you're starting to see a little bit more wiggling, a little bit more flexibility. So let's continue to do that. Where we have cubic splines, I'm going to add a knot every 0.3 instead of every 0.5, and then I'm going to add a knot at every 0.1 instead of 0.3. And if we graph all of those, you can see that you start to get closer and closer to the true fit of the data. So notice the black line. So when we have a knot at every 0.3, okay, it's a little bit harder to see, but you got the orange line that looks like this. Pretty close in a lot of areas, starts to get a little bit off, especially in the middle over here. but generally the curve is fitting pretty well. And then once you get to having a knot at every 0.1, you are sort of getting closer and closer to the black line. So you can see that the green line really overlaps with the black line pretty well, going from end to end. And it's in fact doing a sort of better and better job as you get more and more knots. You'll also note, right, so this is not a natural spline, this is just a cubic spline, so you still have some weird sort of squiggly stuff happening at the end here where it's not following what the black line is doing all that closely. Okay, so there's a question, where in the code does it specify that it's a cubic spline? So when you do this transformation, the basis function for a spline, that basis transformation is coming from the spline packages. And as I was mentioning before, the basis transformation function is basically most commonly used to be cubic. And so that's kind of the default value. I'm not actually sure if you can change the basis function as one of the options. We can take a look really quick. Yeah, okay, so right here, degree equals 3. So the degree of the piecewise polynomial, the default is 3 for cubic splines. So I didn't explicitly type it out, but you could here. I could say comma degree equals 4 if you wanted like a, what is a quartic, a quartic polynomial. Okay. So now, let's take a look at an example where we go really far to the extreme. I'm going to, I'm going to run another, I'm going to run another function or another spline model, regression model, where I have a knot at every 0.0025. So this is going to create a crazy number of knots, right? And let's take a look at what this looks like. So notice, right, the computation time as I increase the number of knots is quite a bit larger. Okay, let me include the true function in here. Oops. Okay. What you'll start to see is a little bit of overfitting, essentially, because the black line, it's starting to look curvier than our true function. And we should be able to, I'll show more sort of extreme examples of this in a little bit. But already here, the knots are starting to you're starting to get to a number of knots where the fit of the line is increasing the variance beyond beyond your true function. For cubic splines, one of the difficulties here is that with the knots, you typically are if you're trying to locate a specific position, in this case, I've sort of set them out uniformly, but it may make more sense to be able to identify specific positions in which to put your knots. And by being strategic about that, you can reduce the number of overall knots that you're using. And the techniques that we've talked about with with choosing a number of knots isn't going to actually help you choose the position of the knots. And so you could just have it uniform and then run the model or cross-validation with differing number of knots that are distributed uniformly, and that could get you where you need to go. But the location of the knots would be sort of like a second dimension of testing if you wanted to do like a cross validation. You'd have to test across two dimensions to be sort of optimally choosing those. The nice thing about natural splines is that the built-in functions will do that for you sort of automatically. So because they sort of have to have some operational aspects of smoothing the endpoints, as I was talking about, then they're able to employ that in the selection of the knot location. And so it's the algorithm of the natural spline takes care of that for you. So we had BS as the basis function transformation, and NS is the natural spline basis transformation. And here all we have to do is X and then the number of degrees of freedom that you want. So this is pretty similar as before, but it's doing some of this extra modification to get the ends of your regression to be lined up a little bit better. And so we can do a similar type of thing where we are predicting this model with natural splines. And so let's take a look at what that looks like. And let me include the true function. So this is our example with a natural spline. Again, here I only have 10 degrees of freedom, so it's not going to be lined up super closely. But as I increase the degrees of freedom, we should be able to see it get closer and closer. So here I'm going to increase to 15 and 30. And so let's take a look. So red is with df equals 15, and you can see the fit is somewhat close, but still sort of shifted off a little bit. Okay, I see. Question. So Jean is asking, what's the degrees of freedom in this context? That's the number of knots essentially. It's a little bit more than the number of knots. I think the degrees of freedom will also include so every time I add a knot, you're increasing the degrees of freedom, but also the transformation that they do at the endpoints is going to be is also included in the additional degrees of freedom. So this represents the number of knots plus some of the endpoint transformations. And when you look a little bit closely at this orange one here, you'll notice that it doesn't do that weird squiggly thing that we saw even in the cubic splines. So really, the orange line is lined up quite nicely with our true function, right? And you should be able to match almost any curve pretty closely as you simply just increase the degrees of freedom. Let me see. So let's take a look at what happens if I go really crazy with the degrees of freedom or the number of knots. I think is the one. This is the one. Yeah. Okay. So I think here you can see what happens as you add too many degrees of freedom, right? You start to get closer and closer to the points in the actual data. And this is where the variance and noise of the function of the data sort of override the fit to the true function. This is where you're getting a lot of overfitting, right? And so again, the way in which we avoid this is to do out of sample cross-validation. Yeah. Okay. So there's a question in the chat: how do you decide the appropriate number of degrees of freedom? Same answer as before for basically any of the other models that we've been looking at, right? So the way we avoid overfitting is to do cross-validation out of sample, looking at the prediction values. So if I were to run this model in a k-fold validation context, I could alter the number of knots that I'm using in my degrees of freedom, and I could get a fit that looks like this versus, a fit that looks like this. Okay, and if I were to do only in sample, then the blue line would actually do a lot better than the orange line because it is estimating on the data that you trained on. But if you exclude some set of points, or if you are able to generate new sort of set of points from what we know is the true function, then the bias variance trade-off allows you to identify the closest thing to our true function. So something that would be a lot closer to the orange line than the blue line. So again, that that technique that we've been learning about with cross-validation is really going to help in this context, right? Especially as we get to these non-parametric models, which allow us to like really closely fit the data. You need some method in which you avoid increasing the error term from variance too much. And that's why, again, a lot of emphasis is put on these validation techniques that will allow us to avoid this blue line. Okay, why don't we take a quick break and let's start up in say 4 minutes. So 11:06.
Hey, Alan.
Hi.
Yeah, hi. Good morning. Yeah, I had a quick question on splines. So, suppose we are looking at a variable y that is dependent on, say, two or three variables, two or three explanatory variables. And out of that, one explanatory variable is the one we know that is going to have a spline fit with y. So how do we go about modeling such a scenario? So you just take y and x to start with, build a model, maybe a spline model for that, and get the coefficients of x, and then plug it back into the original model with all the variables. Or
Wait, how do you know that it's going to be a spline versus the other ones?
no, I don't know actually. Suppose I know that say VMT is dependent on. Suppose I say fuel consumption is dependent on VMT, the type of fuel, and dot 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 so many variables. Out of that, suppose I have a feeling that this is not linearly fitting when I do that, and I take one variable at a time. I see the data, plot it, and see, and I find that with this particular variable, a spline is fitting.
Mm-hmm.
So then, how do I go back into the main?
Yeah.
Does the spline model give you a coefficient value or something like that?
Yes, it does, but it doesn't mean anything, right?
Okay. Mm-hmm.
So, I mean, that's what I was trying to show here. So,
So spline models are meant only for maybe a single variable, a single explanatory variable.
no,
No.
not at all. So actually,
Okay.
so here, so these are my 10 basis functions. And these are the coefficients for each of these, for each of the basis transformations.
Mm-hmm.
But they don't mean anything, right? Like what does 2.7 mean, right? This is some weird cubic transformation that has these edge constraints. It so there's no interpretation here. It's literally just trying to fit this as best as possible. So you can imagine that if I have multiple variables, I can combine them inside spline basis functions in many different ways, and it's just increasing the degrees of freedom. So I'll show. I'm gonna. So these spline functions, when it comes to interpretability, I mean, it's really just figuring out what variables can be transformed to get as close to your data as possible. So I think when you have a variety of variables, figuring out what combination of variables and which ones to use in splines and how many knots to use becomes a pretty difficult problem because you are operating with many degrees of freedom. So there's something that I'm going to show later on in this lecture that attempts to balance the interpretability of having multiple variables and sort of exploiting some of the power of the splines. So I'll say hold off on that question, and we'll take a look at how to address that in a bit. Okay. So let's go back.
Sorry, my network just got cut out. I'm sorry.
Okay. Did you hear
Okay.
anything that I said?
No, I'll come back and I discuss that later on. I'm sorry.
Okay. I'm gonna show something that essentially, hopefully, I think answers your question, and I'm hoping I can get to that by the end of class today. But if not, we'll talk about it at the start of class next class.
Great.
Okay. Let's jump on back to the whiteboard. And I'm going to talk about one more type of spline. And this is called a smoothing spline. Oops. Okay. So smoothing spline looks something like this. Okay. We have this yi term, which is going to be including all of the basis function terms that I was referring to. So you have, this includes, so it's a function of your beta 0, b1, b2 of x1, right, of your x's, and so on and so forth. But now you've got this extra term over here. And so this may remind you of something we've done before, right? So the ridge and lasso regressions, we have some extra term that is going beyond, which is going beyond just the typical reduction of the sum of squares. So what is this function here? It is the spline cubic function that constrains the first and second derivatives to be continuous. Okay. And so, okay, wait, I think I misspoke. This isn't quite the thing that this part isn't quite the thing that's like the last one, Rich. We're gonna get there in a second, but this is the portion where the cubic function is trying to make things basically as smooth as possible. And that can be, modified in certain ways such that it reduces your RSS term, right? And that's essentially what the spline regression is trying to do. So let's suppose you had a knot for every point. So that might look something like, if I had some series of points, if I had a knot at every single x in my data, then you can imagine that the spline function would do, something like that, or it could do something like that, right? Because we have so much flexibility in the number of knots. So this perfectly minimizes the RSS, but you have overfitting. Okay. But you could imagine that I could draw this line in many ways, right? I could do something like that. I could do something like, I could do something more extreme where I could go like this. And so all of those are different ways in which I fit all of my points as I go through all of these knots. And so as I went from blue to black to red, the sort of curviness of each of the lines, I'm slightly decreasing, right? Whereas I might jump around quite a lot. Like here, you can see that in the red line here, it's not nearly as kind of wavy. And so you are actually able to modify the way in which the knot at each point is being how it's sort of connected from point to point, and how curvy it gets, essentially, right? And the way that these knots again are formed are by making your first and second derivative continuous. So the way in which you can decrease the curviness is by reducing the size of the second derivative. So let's shrink the second derivative, which prevents your line from going super crazy, like in the blue case. So this is where it's similar to our ridge and lasso regressions. So in addition to this term, we're going to add a tuning parameter. So this is our tuning parameter. And then this is our penalty function. Okay, so the larger our second derivative of our cubic spline is, then the larger the penalty is. And so there's a balance happening here between how our cubic spline function allows us to fit to our actual data here compared to if you make the line essentially too curvy, then it's going to penalize our objective function here. And the weight of that penalty is based off of our tuning parameter. So really, this is just like our ridge regression. So like the ridge regression, this penalizes the function by encouraging smoothness. So rate of change of slope should not be so big. So if I were to get a bunch of points at a low tuning size of my tuning parameter, I may get something that looks like this. And if I take the same set of points, at a high value for sigma, it may look something like that, right? And that's because we have penalized the ability of my spline to jump around a lot. And we want to emphasize this sort of smoothness as opposed to something like that. Okay, how do we select our tuning parameter? Same song and dance, right? Cross-validation. So the way in which we select our lambda is going to be same as you would do in your ridge and lasso regression, and same as you're doing to select these parameter values across many of these different models. So you want to get the best out of sample fit as possible. Okay. So let's jump back over to R. So this should also be contained in the spline package. We're going to smooth a spline on X, and our Y is equal to Y, and the S bar, that is the tuning parameter, and you can set that to values between 1 and 0. Okay, and so as a reminder, right, when your tuning parameter is really large, the penalty function becomes extremely important, and it makes it so that that it wants the line to be as smooth as possible. And when you have it at 0, you have you allow for the line to be unconstrained in terms of the penalty function. And so remember, with a smooth spline, we have it's going to be the same as the previous splines that we've done, except that you have a knot at every single point, and the penalty parameter is just allowing for how much smoothing is happening at every knot. So let's take a look at what this looks like. We can go one at a time, actually. Okay. So in the first one with a penalty function that's extremely large, you can see that the line basically becomes flat, right? Because essentially the model is saying, well, the trade-off that I'm making here for smoothness, which I'm really putting an emphasis on, I don't allow the knots to vary much from sort of point to point. So even though you have knots at every single point in here, the line ends up looking pretty straight. So now let's see what happens as I tune down the penalty function. Okay, so here the line essentially it's allowing for more and more curvature because it is decreasing the penalty for smoothness. And so let's see what happens here. Okay, and so at a penalty function, at a tuning parameter value of 0.5, we're already getting, fairly close to our true function. So now let's further change the tuning parameter to 0.25. So that's the orange line, and here I guess you start to see a little bit of overfitting, right? We see, especially in the center here, we see a lot of squiggliness, and you can imagine what happens with the last one. So this is a totally unconstrained spline function where you have a knot at every point. And so it looks something like this. Okay. So the last thing that I'll say is that the smooth spline, so normally you could run this through a generic cross-validation thing, but the built-in function actually includes that for you if you wanted to, so that you don't have to figure out what the tuning parameter is manually. And so the option to do that is just CV equals true. And so when it does this, it'll select the best tuning parameter automatically. I can run this and see what that looks like. And so let's see. Yeah, so in the red is my true function, and in my blue is the spline function. So you can compare this against, the previous nonlinear models that we've looked at, with the polynomials or with the stepwise segmented, or piecewise, not stepwise, piecewise regression. And you'll note that, these splines tend to do significantly better. And once you have a knot at every point, which is a sort of fundamentally different way of approaching it compared to the cubic spline functions and the natural spline functions that we were talking about before. Here we can see the fit is doing pretty well, right? Okay. So, as I mentioned before, sort of in practice, these splines are a really sort of powerful tool that allows you to get highly nonlinear, non-parametric fits of data, and they can fit very closely to true functions, right? And so you can see here the blue versus the red, they're basically completely overlapped. But the sort of trade-off that you're making here is that as you depart from any sort of specified functional form, the interpretation of what the spline like basis function does is not something that you'll be able to do, and so inference of these type of models is not so useful compared to its ability to predict. So that having been said, is there any sort of way in which I can maintain some level of interpretability, or suppose that I have, multiple variables. You can imagine that the combination of degrees of freedom and whether I select certain variables to do basis transformations, and the extent to which, I have added, penalty functions or choices of knots and so on and so forth. That can get really complicated as you go to multiple variables. And so I'm gonna talk about a sort of in between approach where it's not sort of totally non-parametric combinations of all your explanatory variables, but it allows for additivity of explanatory variables while considering doing some splines on certain variables. Okay, and so let's jump back to the whiteboard. So this is the technique that kind of employs combinations of strengths and weaknesses across the purely sort of non-parametric versus parametric models. So this is known as general additive models. So maintains same interpretability by additivity of terms. So this uses a spline for each individual variable and adds them together. Okay. So the formal transformation of your linear regression looks something like this. Plus dot, dot, dot. So our yi, in this case, okay, we still have an intercept, and now we have this smoothing function here, which is essentially additively modifying each of my explanatory variables into splines if I so choose. And so the combination of those basis functions that I was showing before can be applied to each individual variable, and then you can look at that in an additive way, so that you're still looking at this form of a linear additive model. Okay, I think I missed a question in the chat. So does spar in the code represent the lambda tuning parameter? Yes, that's right. So I'll jump back to that in a second, so that we can see. Actually, we'll just go ahead and jump back into R. So I'll show what the general additive model is doing. Okay. Yeah, so this was the previous question here. This spar thing is exactly the tuning parameter. Okay, so we're going to jump back to an example data set that we can apply our general additive model to. So we're going to use the hitters data that we've looked at before, and we're going to use a library called MGCV, and that contains the function called GAM, which is your general additive model. So similar structure as your linear model. So I can type in variables like such, but I can also add this little bit, S, which means that I want you to smooth this particular variable with a spline. So I'm going to do that for everything. Actually, I'm just going to copy and paste this. Except for my for categorical variables, you can't smooth it, obviously, because it's a discrete set of values. But otherwise, for all of my continuous variables, I'm going to put this little option here, S, which is going to smooth it out as a spline. And let's take a look at the summary. Nope, didn't load the data. Okay. And so, in fact, here we can see parametric coefficients. And so these are your regular linear coefficients. So this would be the same interpretation as a linear model for division and for my intercept. And then for my spline functions, it's showing this information, which tells you some sort of statistical significance, difference from 0 type of thing. But otherwise, it's not providing any necessarily interpretable coefficients. So here is, I think, where we can see the usefulness of doing this kind of approach. Okay. I never liked the sort of format in which they're showing this. These are the spline fits against my response variable. So the y is the salary, and then the x is each of these variables. And then you can see these little tick marks down here at the bottom. And so this indicates where this indicates each data point in my data set. And the reason for that is because this oftentimes extrapolates values to points where you don't have a lot of data. So you're getting to some of these outliers here. And this gives the spline fit for each of my individual explanatory variables. Principally, I think that this is a nice thing to do in many situations. So even if you don't end up doing a general additive model for everything, this can be a really good way of verifying whether or not the trends in the data actually are linear, right? And so we run these linear models all the time, and one of the least common tests to check is whether or not the functional form of the data makes sense and matches with our linearity assumption. And you can see that here, right? And so if I were to look at maybe putouts and CRBI, these look approximately linear. And so if I were to leave these as just a typical linear variable, I think that the coefficient estimates would line up with these fairly nicely because they're approximately linear. But if I look at something like hits or walks, right, these don't look very linear. And so if I were to do like a regular linear model with all of these variables, well, this one, the C walks and C hits, is probably biased. So you could actually always go back into here, and I could, because I've taken a look at this, and I said CRBI and putouts are both linear, I can actually remove the smoothing portion for just those variables. I can run this again. I can take a look at the summary. And actually you'll get regular coefficients for those two variables. And in fact, if I look at this estimate and I compared it with the previous plot here, that slope of that line and the slope of this line are probably going to be pretty close to these values here. And if I plot this again, now we can see the remaining variables and their spline fits as sort of captured from before, but now we have a combination of our regular non-transformed linear variables of CRBI and putouts, and we also have these sort of spline fits, all of which don't look necessarily that linear. Okay, so this is, I think, regarding Vishnu's question about if you have a whole bunch of variables and you're unsure about which ones need to be smooth and how to select them in sort of combination. I think that the general additive model is kind of the nice compromise sitting in between, your purely all non-parametric functions where we do everything in splines, and you combine all of that into sort of a single fit against your data, compared to your purely linear model where you assume the functional form is all linear. With the GAM fit, it assumes that everything is still additive, which lets us separate all of the individual variables and lets us smooth explanatory variables sort of one at a time, and it lets us identify whether the relationship between our response variable and our explanatory variable is actually linear. And again, to emphasize, I think that this is a really nice way of testing out your linearity functional form assumption for your regular OLS models. And so I typically like to encourage that, if you run a linear model, you always have a quick go at doing a general additive model just to see whether or not your linearity assumption even sort of makes sense. And if I were to just, if they do all look linear, I could, in theory, just remove all of these S's, and then the model would look exactly the same as a regular linear model. Okay, and so regarding sort of the pros and cons of this approach, is that it is balancing between sort of the predictive aspect of your pure non-parametric approaches with the interpretability of your linear model. So I still, if I look at the summary thing, it's not giving any, these are all diagnostic terms with relation to your spline output, but it doesn't say anything about the interpretability of like a coefficient or anything. But what the additive model does allow you to do is that you still can give some interpretation, because I can look at these lines and see how changes in my explanatory variable will relate to changes in my outcome. And because it's separated individually, you can see that effect variable by variable. Okay, there's a question coming up. Does this function is this function doing a combination of linear and nonlinear regression methods in the same regression? Yeah, that's exactly right. So this is sort of what we've been building up to, because this S thing is essentially doing a smoothing transformation of your variable, and it's it's not necessarily the combination of linear and non-linear. It's more of which variables it's choosing to smooth, and it's making it additive so that you can interpret each individual variable separately. Okay, so this is, I guess, the end of the lecture for today. I will mention that the last homework is posted as of today. So that's it'll be, I think, a little bit shorter than the previous homeworks. So that should be nice for you guys, and it'll be covering up to, I believe, this lecture, and the homeworks will be due next Thursday. With regards to the projects, I am about halfway through going all of the proposals, but I'm hoping to be able to send you feedback either today or tomorrow. Some of you guys have already spoken to me in person, in which case, I'm not going to add anything to what we've discussed. But if folks are interested in chatting more about the project, you can either email me or we can chat in office hours. Otherwise, I think that's all we have for today. And I will see you guys on Thursday. And again, I'll stick around for a couple minutes for any questions that folks may have.